In this video, we will talk about forces. Forces are one of the few concepts in physics whose basics are familiar to everyone. Forces can also be quite confusing and complicated. Let us learn the principles behind forces. The classical understanding of forces that we often learn in introductory courses first appeared in Newton's magnum opus titled Mathematical Principles of Natural Philosophy, often called Principia. Several of these ideas are not originally from Isaac Newton, but from other scientists such as Galileo Galilei and Robert Hooke. Instead, what Newton did was to infuse the already prevalent ideas about forces together with experimental and observational data, giving them solid empirical foundations. What are these ideas regarding forces? First is the superposition rule. A set of external forces acting upon an object can be mathematically represented by a single net external force. The net external force is the sum of the net external forces acting on an object. The net external force does not exist physically, but its effects on the motion of the object are physical and real. Second is the concept of inertia. It seems to us that motion needs a sustaining force to continue. The first law says, no. Everybody continues in its state of rest, or of uniform motion in a right line, unless it is compelled to change that state by forces impressed upon it. A force is not needed to maintain the motion of an object already moving at a certain velocity. Not only that, objects have a tendency to resist any change in its velocity. We call this tendency as inertia. The physical quantity that represents this tendency is called inertial mass. The more massive an object is, the better it can resist changes in its velocity. Given these facts, how do we make sense of the fact that all motion that we are familiar of here on Earth eventually comes to a stop? An object slowing down means that the velocity is decreasing. This implies the existence of a force that resists the motion of an object. Instead of considering it as natural state of things on Earth, the first law of motion predicts the existence of resisting forces. Resisting forces are not always undesirable. They are life-saving when you jump from a flying plane and then deploy your parachutes. The resisting force involved here is called air resistance. Air resistance is proportional to the area of the surface facing the direction of motion. The bigger the parachute, the stronger the air resistance will be. Resisting forces are also life-saving when you suddenly need to stop your car by pressing hard on the brakes. The resisting force is called friction. Friction depends on the surfaces in contact. Friction is both desirable and undesirable for a car. Friction between the components of the engine shortens the lifespan of these components. We apply lubricants to minimize it. Friction between the brake pad and the wheel ensures that the car will slow down when you step on the brakes. The third idea is that forces cause acceleration. We defined acceleration as the change in velocity of an object. This makes sense. To make an object start moving, we push it to the desired direction. To make a moving object stop moving, we push it to the direction opposite to its direction of motion. We can therefore say that the force is proportional to its resulting acceleration. We finally add inertial mass here, and we have the mathematical definition of the second law of motion. Interestingly, this is not the original statement of the second law of motion in Newton's Principia. He defined the second law of motion as follows. The change of motion is proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. Newton defined the so-called quantity of motion as the product of mass and velocity. We call this nowadays as momentum. A moving object has momentum. We now get the following as another statement of Newton's second law of motion. The net external force is equal to the time derivative of the momentum of the object. If we apply the rules of differentiation to the equation, we will come up with two ways of changing the so-called state of motion of an object. The first one that we have mentioned is by applying external force. The second one is by reducing your mass. It sounds fanciful, but this is the physical basis of rocket propulsion. You throw a certain amount of mass so fast, you will also start moving. More to that later. The fourth idea is that there is always a pair of forces that act between two interacting objects. This is enshrined in the Newton's third law of motion. This is mathematically expressed as follows. The suffix A on B means that the force is applied by object A on B, while the suffix B on A means that the force is applied by object B on A. As these two forces are applied on different bodies, they do not cancel out. To better understand this, let us consider walking. Why does walking work? What our legs and feet do is to exert a force on the ground. The ground at the same time exerts a force on the legs and feet, pushing us forward. So we actually manage to move while walking because the ground exerts a force on us. The same thing happens to rockets as they fly to outer space. The hot exhaust gases exert a force on the rocket, accelerating it forward. In return, the rocket exerts a force on the gases, further pushing it away from the rocket. These are the three laws of motion as enshrined by Newton in his Principia. These principles serve as the foundation of classical mechanics. Question: does the choice of reference frames affect our analysis of forces acting on a system? Yes. These laws of motion are applicable only on inertial reference frames with constant velocity. If the reference frame is accelerating, a fictitious force arises. This force does not exist in all reference frames. They only exist in the accelerating reference frame. Fortunately, the fix is simple. A term to account for this fictitious force is simply added to the original statement of the second law. Question: were the Newton's laws of motion proven wrong at least once? Yes. Thank you for watching. See you soon.